Thank you, Mr. Shu, for that introduction. That good day joke, I still remember walking into class to that several times when I was here at Sycamore, so I'm glad that hasn't died. So my presentation is on the intersection of music and cognition. And this was a kind of a shortened version of a larger project I did at Park Tutor over kind of a 2-year span where we get to pick a topic of our choice and research it over a whole year. And that was, of course, about music and nostalgia, as Mr. Schuth mentioned. And as I was working on that, I was kind of reminded of my experiences at Sycamore. In particular, I was reminded of our 8th grade current event research project in Mr. Young's class. And of course, everything from MLA citations with Miss Simpson to just kind of learning the basics of an essay in Miss Kohler's class. So I'll start on what is music and how do we process it. So music's kind of hard to define. For the purposes of my project, I defined it as the arrangement of sound in a way that creates some kind of form, beauty, harmony, or melody. Unfortunately, that's still a pretty subjective definition, but music has some shared elements when it's broken down that kind of help us identify it. Pitch, rhythm, tempo, or key are kind of included there. And in terms of how we process it, there isn't really a single area of the brain that processes music. Scientists used to believe that the auditory cortex was the only part involved, which kind of makes sense until you break down what music really is. And music really is just a collection of vibrations. So apart from the pitch of music itself, like the key, the sound quality and the tone of different sounds affect their wave patterns, and therefore they affect the way that we perceive the music that they produce. So this is kind of a graphic on different vibrations. These are 4 different instruments that are all playing the same piece of music at the same volume, but you can see through the differences in the vibrations that they are in fact producing different sounds, and that's kind of how you can differentiate between the sound of a piano or the sound of a violin. And so in the ear, kind of a more anatomical look at things, sound waves hit the outer ear and cause vibrations in the eardrum and in the middle ear. And the middle ear is kind of that green area. And after it hits the middle ear, it will pass through the tympanic membrane and into the cochlea, which is that snail-shaped thing. And inside the cochlea, there are thousands and thousands of hair cells that can interpret and process the pitch and the tone. They're tuned to specific frequencies, and those vibrations kind of are translated into signals that are then carried up to the auditory cortex through the cochlear nerve system. And there you can see the cochlear nerve at the very end of the diagram. And something interesting that I wanted to share with you was the way hair cells are kind of oriented in the cochlea. They're kind of ordered like piano keys. And they're laid out in terms of pitch, so the frequencies will get higher from the front to the back, sort of like on a keyboard. More generally, though, I wanted to talk about music inside the brain. Our auditory cortex processes pitch, so the sound and the tone, and the motor cortex and cerebellum help decipher rhythm. And something that's interesting about that is because they are motor regions, they kind of monitor our movement, and that contributes to this kind of phenomenon of people tapping their feet or drumming their fingers to a beat without being aware of doing that. That's because the motor regions and the regions that process rhythm are overlapping. And then the hippocampus and amygdala are involved in memory and emotion. Those are shown in very small dots on the right side. The corpus callosum is in blue. That I wanted to bring up because scientists have found that it develops to become larger in musicians. And the corpus callosum controls the connection between the 2 brain hemispheres, where the left brain handles problem solving and logic, and the right brain handles creativity and imagination and that sort of thing. The rest of these structures mostly deal with playing music, so I won't talk about that much because my project was mostly focused on listening to music, but I will continue to talk a little bit about memory, which will connect to kind of Alzheimer's disease research and some of the stuff that I did in high school. So music and memory is kind of a special connection because music is uniquely able to stimulate memory and stimulate very intense recollections of memory. It's a common kind of phenomenon that happens among Alzheimer's disease patients where they might forget their own name or the people around them or just really significant aspects of their life. But if you play a piece of music for them, they will be able to remember it, or they might even be able to hum along. And in some cases, they can even play pieces for you, even if they can't remember anything else. So I want to explain a little bit about how that happens or why researchers think that might happen. Some researchers have kind of hypothesized about a musical memory area in the brain. This isn't confirmed, but it's a pretty interesting study nonetheless, and I think it connects a bit to some of my research. So what they did was they looked at healthy individuals and their brain activity as they were listening to music. And they identified a few brain regions that were active while these young, healthy individuals were listening to music. And as they identified those areas, they took note of them, and then they compared it to the brains of people suffering from Alzheimer's disease or dementia or mild cognitive impairment. And they found that some of the areas that lit up when people were listening to music overlapped with areas that weren't harmed by the effects of Alzheimer's disease or dementia. And so researchers think that there might be a musical memory area that is left largely unaffected by that disease. And so this diagram shows 3 biomarkers of Alzheimer's disease: gray matter atrophy, amyloid buildup, and low metabolism. And a biomarker is basically, it's just a marker of a disease that shows up in your biology, basically. So amyloid beta, for instance, is pretty famous as a biomarker for Alzheimer's disease. It's basically just a protein that builds up in the brain, making it difficult for people to remember things or have fully functioning cognitive function. So some of my research revolved around biomarkers. I first started off looking at epigenetics, and that was kind of an interesting connection to my time at Sycamore because in Mr. Schuth's class, I remember talking about CRISPR because at the time, CRISPR was first becoming used popularly, and we were all kind of buzzing about it and talking about it, and I remember thinking that was something really interesting that I wanted to look into more. At the time, I didn't really know how I would go about doing that, but I was in middle school, so I wasn't too worried about it. And something else that I think is kind of important lesson from Sycamore was that, I'll start with another story, I guess. Also in Mr. Seuss class, we were talking about neuroanatomy, and the entire time I remembered thinking, this is really hard and I really don't like it. But look where I ended up. So I think it's important to kind of still consider things that you don't like as much immediately, because sometimes you'll find that you end up really loving it. I ended up really loving combining those two things, looking at genetic changes in the brain, and that ended up kind of moving my research forward. So it was sort of a combination of something that I thought I liked and something that I thought I would not like. And so my research, I'm getting kind of off track, but coming back, my research was about inflammatory biomarkers. I first started looking at genetic changes that occurred in the brain. I was specifically looking at the regulation of neurogranin, which is another biomarker of Alzheimer's disease, kind of similar to amyloid beta. It's another protein that builds up as you age. And then I sort of ended up working with a group in Sweden after reviewing a lot of papers. There is a lot of stuff from that group in Sweden. And I kind of contacted them. I asked if they might be able to work with me or maybe just review my paper, see what they thought of it. And I was able to work with them on some inflammatory biomarkers. And that's kind of how I went about my Alzheimer's research. But kind of coming back to the music aspect of things, I wanted to talk about this kind of interesting phenomenon of earworms. It's a little bit off topic, but I thought it would be something that you would enjoy. It's this unique phenomenon where music is able to pierce our subconscious, and it's very unique to music, unlike any other kind of information. Some people find that maybe images might stay in their memory involuntarily, but earworms or pieces of music are kind of the only piece of information that really gets stuck in our head and kind of repeat in our head involuntarily. And this is kind of why some scientists think there is a really unique connection to music and memory, because this is kind of something that pierces our subconscious. We're constantly listening to music. Almost 70% of people's waking hours are spent listening to music, and so it really stays in our subconscious, and we're much better at remembering it and recognizing it, and that might explain why we retain it so well. And then kind of connecting to emotions and addressing more of the brain and its connections to music. Emotions, unfortunately, do kind of boil down to a few chemicals in our brain. These emotions are often induced by neurotransmitters like dopamine or serotonin, and those might induce feelings of happiness or pleasure. And they're primarily stimulated by visual cues or auditory cues and such. But while some researchers believe that music is only effective for stimulating happiness or fear or sadness, we've actually been able to map 13 different emotions into different, in response to different types of music, and that can range from anything from amusement to dreaminess to anxiety and to annoyance to those three emotions that I first mentioned. So this kind of shows the span of impact that music can have on our brain in just one section of our brain, which would be emotions. And another thing to consider here is how music is reflected in emotion, or vice versa, how emotion is reflected through music. And what I mean by that is it's hard to determine whether music triggers emotions or if emotions are more triggered by music. So for instance, when we listen to happy or joyous music, our zygomatic muscle, which is what we use to smile, is often triggered. And when we listen to sad or depressing music, our corrugator muscle, which is what we use to frown, is often triggered as well. And so we know that our body will unconsciously react to music. And the reason that's interesting is because we don't really know if these reactions have developed because of music or if music reflects our kind of anatomical reactions. So we do know that as very young children, our neurons are kind of free. And then as we grow up, we develop connections and associations to certain music and certain feelings that kind of dictate how we feel about certain music. But we don't really know which came first because we don't know when we first had music. And so that kind of connects to music throughout our lives, talking about neural connections throughout our lives, and as we develop how we create certain associations with certain kinds of music. We know that in the NICU, for example, in intensive care units for young children, listening to music can often help babies have enhanced connectivity in different brain regions and decrease their stress. So often listening to music in the NICU will cause children to be able to get out of there faster. And we also know that in our teen years, the music that we listen to in our teen years often sticks with us throughout the rest of our lives because of the intense hormonal changes that are happening and the way that our brains are being remodeled in those years. That contributes to very strong connections to music. And of course, connecting back to Alzheimer's disease and cognitive decline, music has had very significant restorative effects on individuals with mild cognitive impairment or Alzheimer's disease, as music therapy, either listening to music or playing music, has kind of helped redevelop a sense of belonging or a sense of not feeling out of place in those disease cases. I want to talk a little bit about evolution because, as I was saying, we don't really know how long we've had music or whether music reflects our emotions or if it's the other way. And we're also very uncertain why music is remembered so well, even though we forget other information that should be essential to us, like our own name or the people around us. We're really kind of unsure as to why. Some researchers believe that we've had music longer than we've had language, and that early Neanderthal ancestors actually were communicating with pieces of music rather than actual language. They were using kind of holistic phrases to communicate with each other rather than language, and that might explain why we remember music so well. And we also know that music and the brain have kind of co-evolved. Music has changed over time along with our brains, and our emotional capacity largely parallels our music capacity because of this. For example, a lot of scientists believe that we have an innate sense of musicality. Knowing what is considered dissonant or what is considered harmonious is not something that we completely learn. It's something that a lot of us know already as very young children or even fetuses. And so that's kind of an interesting aspect of evolution in terms of music and the brain. And it's not really something that's talked about often. I think music is very underrated in terms of being used as part of scientific study. And another final interesting kind of evolution-related thing is string theory. This is still kind of hasn't been scientifically proven or disproven, but according to the theory, the fundamental ingredients of matter are very tiny vibrating loops, kind of like when violin strings are bowed. And the point of kind of string theory and the musical argument anyways is that music is tied to the heart of matter. And scientists have actually found that the universe itself has a pitch, but this pitch is too low for humans to actually hear. And so they're thinking that this might be a part of a subconscious or internal physical reason why sound and music, and especially pitch, have become so important to us rather than just lengths of sounds or the rhythms they make. And so key takeaways about my research and kind of this larger project. Neuroplasticity, it's kind of just defined as the brain's ability to change over time. Neural connections they exist in every single part of the brain, especially when we connect to a piece emotionally, and that might contribute to why we remember music so well, and why music has such a strong impact on our brain. Universality, what I mean by that is just kind of how music seems to have a relatively universal effect. People around the world are able to listen to music and experience the same emotions as a result of music. Even if they are isolated from certain types of music. My example for that is researchers kind of met this Cameroonian tribe who were isolated from any form of Western music, and they were asked to listen to music and assign it to 3 images that depicted fear, sadness, and happiness, and they were actually able to respond accurately to at least what Westerners would have agreed with were the intended emotions that music evoked. So that's kind of an interesting aspect of how music affects us all universally. And finally, evolution. The evolutionary purpose of music is still highly debated and researched, but we do know that there is some kind of connection there, and we still wonder why music has evolved this way and not something else. And I guess one last thing that I wanted to say was about kind of what I learned at Sycamore and something that might connect to you a little bit more is it's hard to know what you want to do with the rest of your life, and even I don't know. I'm only a senior in high school. But I think it's important to not only look at the things that you are currently really interested in. For instance, for me, it was genetics at the time, but also to not forget the things that you aren't as interested in or even have said no to entirely. In my case, neuroscience, because you might find that that is something that you're interested in if you are able to learn more about it. So, yeah, that's all I have. Thank you.